So this is lecture 23 in section 4, the ensemble models and module 2. So in module 1, we introduced the basics of ensemble method, which includes 3 different kinds. So bagging and boosting and stacking. So in the module 1, we introduced bagged decision trees. So now in module 2, we will explain in details random forest.
Okay, so random forest. What is random forest? Random forests use decorrelated trees. That's the fundamental idea. But in fact, the whole procedure, the pipeline, is almost the same as bagging. The only difference is, so I'm still doing bootstrap sample of my training data to get S1 onto SE, and each one of them have the same size as the original training data. And different now is when I'm trying to do the splitting, rather than consider all the P features, I'm trying to get a random subset of features, like M features out of the P. I only pick splitting features from that M subset. For each split, you perform a feature subsampling, and then you pick the best among that M. So in the end, if you think about it, so this level of bootstrap adding randomness of training data, and this level adding randomness of features. All right. So same thing as before, you grow B different trees, and specifically the specific random forest always is a binary tree. So I did not cover there's the variation of trees last time. So in fact, there are a lot of different kinds of basic decision trees. ID3, C4.5, CART, and random forest, the specific random forest people normally use is built on top of the CART decision tree based learning. So I have some extra slides in the previous decision tree lecture. Feel free to check out. So what makes the differences of ID3 versus C4.5 versus CART? So there are actually quite some differences what they make. And also the specific random forest, the splitting measure it used is Gini impurity measure. It's not information gain. Information gain was mostly used in C4.5 type of decision tree learners. But they're actually very similar to each other. If you remember, they all have this kind of bell shape. I mean, top, the more uniform the distribution, the higher the measure, the lower on each side is what you prefer. So the pure node is what you prefer. All right, so you grow B trees, B different trees, and at each split, there's only M random subset of your feature are considered. So then you can, again, doing majority voting or doing mean prediction, and it's all can be, it's all supported in the package. All right, so more concretely, so for former tree, when given P dimension, you pick M of the dimension. You split only according to those M dimension, and it's not you're not going to consider the P minus M dimension at all at that split. And repeat this 1 and 2 procedure for every split. So which means for every split, you pick a different subset of M features. Question about this random forest? Sure.
Can you repeat some of the features?
Yes, you actually can. So this, then the very natural question is, so what M? How many M should I use, right? So this, the author actually did a lot of experiments trying to see, give guidance of what M to pick. So it's normally has this kind of plateau. So in the beginning, it gives good performance, and then so in here, good performance means the correlation. So the correlation, the smaller of the m, the lower the correlation among trees. So you can see the y-axis is the average correlation among trees, which is extremely small. It's about 0.06, and then when you have a lot of m, so it kind of increases correlation, and then you normally stop at a certain number, which it's in the next slide, the author has a guidance about what m to pick. So there's a good balance of the number of trees, because the more the tree, the more computational cost, right? We cannot just see, wow, if the bigger the bee, the better. Let me just grow many trees, right? Or many base learners. And there's always the cost of learning cost, memory cost, training cost, and test cost, right? You also need to consider everything together. So, but the correlation, we should actually keep that number here, this rho. So if you still remember what is correlation, so we actually introduced the correlation equations in feature selection lecture. And we know 0.06 is extremely small correlation number. So correlation is from, so upper bounded by 1. If it's 1, it's fully positive correlated. And when it's close to 0, it almost means there's no correlation. And this has a slightly correlation, but very close to 0. And then why do I even care, right? It will be really clear why that rho number is important. So now let's first see, so what's the m values? In fact, if you think about it, when m equals to p, this model is exactly baggy. And normally for regression tasks, people recommend, the author actually did a lot of theoretical analysis to recommend log p or p over 3 for regression choice, and also for classification is square p. So if you want to understand why, actually feel free to read original random forest papers. It's a very solid, theorem-grounded work. So even though you can think about, wow, so it's so simple, right? I bootstrap my training set, I'm growing bee trees, and then I'm putting this together. So intuitive and easy, but there's a reason why you pick m features and how do this influence. The paper itself has a really nice analysis about this choice. Okay, so now let's come back to this original motivation to do decorrelated trees, right? So why correlated trees are not ideal? So I give you a simple explanation from this variance of ax plus by, but more concretely, so what is the concrete formula for the decision tree of a random forest? So let's assume each tree has a variance sigma squared. If the trees are independently identically distributed, then the average variance is sigma squared over b. I actually proved it, right? I used this to, it's very easy to prove, is 1 over b sigma squared. Because correlation are 0, and then the scalar becomes a square because every share the same scalar, 1 over b, and then you have a scalar 1 over b quadratic, and then each one of the base classifier, the variance is sigma squared. You have a total of b such base classifier. This gives you b sigma squared, and then the final outcome is 1 over b sigma squared. Question about this? It's actually very easy to prove this. Yeah, just from the basic axiom of variance equations. All right, so yeah, I should remove this animation, but okay, now let's see if there's a correlation, there are correlation among trees, what is the variance equation? And this actually is the equation of the final joint model if there's a correlation. Of course, you can tell, actually, I'm assuming each pairwise correlation is the same row, but there can be more settled representation, like row 1, row 2, row ij. But let's just assume all the possible row ij means the correlation among fi and fj. Be all equals to rho. And then this is the variance of the f. If you're assuming f equals to 1 over b, a summation of fxi. And this looks pretty weird. So why do I write like this, right? It's actually very easy to see. So when you have more and more b, and this denominator becomes super large, which makes this portion just not matter at all. And then the whole variance of the model is controlled by rho and sigma squared. So which means you really want to decrease the rho and to make the model, to make a smaller variance. Because when rho equals to 1, and this is exactly like the base classifier, right? Your base classifier has sigma squared, and then when you have b, different classifier, their variance still sigma squared. And then think about what is the whole bagging or random forest. There's no benefit it brings me at all. So that's why, and this rho, it's important. When I have 0 point like close to 0, this is a huge improvement over the base classifier decision tree. Okay, question about this? All right, sure.
Is there still any like limit for b? Like we shouldn't increase it more than a specified limit?
Yeah, so good question. So the question is, if the bigger the b, the better. Why not just pick a super large b, right? It's almost that. How do you pick the right b? Yes. So like I just previously mentioned, here it's only about variance, right? But when you have bigger b, there's some other cost. There are actually a lot of cost if you think about it. First of all, data cost. I mean, you sample and then the hard drive, it's b times whatever you have, right? So let's just see RAM cost is times b. Then there's also training costs, right? We always do calculation about what's the training cost for each base classifier. And then this also times b because you do b of those. And maybe training like time, it's fine because you can do, you don't care how fast you train this. But if during the testing, and especially k-nearest neighbor type, right, when you have b such models, and this is actually b times of the inference cost too, right? It's really a balance you have to pick. And you can't have too many b. Of course, if you go Google or Facebook or they just go to the distributed cloud and use as many as b servers that you wish. Those are the good situations. Yeah, but we normally don't. Okay, yeah. But you can tell, I mean, this time of ensemble classifier is extremely parallelizable. And this is actually a benefit if you think about it. Extremely parallelizable. Yeah. More question about this? All right, so let's go to boosting. So so in the end, we reduce the pairwise tree correlation and then because the row gets smaller, so that's why the total variance of my random forest model got reduced. It's very clear from that equation.
Great. So this is the end of this module. See you in next module.